Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to everyone. So, today, my group, which is Group 4, will explain to you about telescope as portal discovery.
Assalamualaikum warahmatullahi wabarakatuh. I'm Anissa Franasuha binti Mak Saleh. So I will start this presentation with introduction. What is telescope? A telescope is a tool that astronomers use to see far away objects. Most telescopes and all large telescopes work by using curved mirrors to gather and focus light from the night sky. The first telescope focused light by using pieces of curved, clear glass called lenses. Why do we use mirrors today? Because mirrors are lighter and they are easier than lenses to make perfectly smooth. The mirrors or lenses in a telescope are called the optics. Really powerful telescope can see very dim things and things that are really far away. To do that, the optics, be they mirrors or lenses, have to be really big. The bigger the mirrors or lenses, the more light the telescope can gather. Light is then constructed by the shape of the optics. The light is what we see when we look into the telescope. The optics of a telescope must be almost perfect. That means the mirrors and lenses have to be just the right shape to concentrate the light. They cannot have any spot, scratches or other flaws. If they do have such problems, the image get warped or blurry and is difficult to see. It's hard to make a perfect mirror, but it's even harder to make a perfect lens. So we move to a second point. It is the purpose of a telescope. By collecting more light, a telescope makes astronomical objects like stars, galaxies, and planets brighter, sharper, and easier to see visually or to image. To collect light from distant objects, a telescope uses a curved lens or mirror called an objective and focus the light to an image at the focal point. The focus image formed by the objective lens of a telescope is magnified by a smaller second lens called an eyepiece. As visual observers, we look into the eyepiece to see the bright magnified image from the objective. But an eyepiece used with a small lens or mirror simply magnifies a dim and fuzzy image. So although magnification is useful, it has no effect in helping you see detail in a telescope. The detail and brightness of an image all comes down to the amount of light collected by the objective lens or mirrors, and that depends on its diameter of the objective, also called the aperture. Like a big bucket collects more raindrops than a small bucket, a big objective collects more light than a smaller one.
Hi and Assalamualaikum. My name is Rizka Najmi bin Abdul Samad. So now I will talk about the history of telescope. Hans Lippershey, the first person to patent a telescope in 1608. According to the legend, he conceived of the idea when seeing two children holding up two lenses that appeared to make a distant weather wing appear closer. Then, in 1609, Galileo Galilei heard about Hans' invention and invented his own telescope within days. Galileo was the first person to find a telescope skyward. He discovered the mountain and craters on the moon, as well as the Milky Way, also discovered the Saturn. Sir Isaac Newton later built the first refracting telescope in 1668. This is the type of the telescope with a mirror in it rather than lenses. In 1789, William Herschel built the largest telescope of the 16th century in the UK. It was a giant reflector with a mirror that was 49 inches wide. Edwin Hubble used a 100-inch Hooker telescope to find variable stars in the Andromeda Galaxy in 1924. This allowed him to scientifically derive that it was outside the Milky Way galaxy. Hubble has contributed so many discoveries to the whole world from then until now.
So next, I am Nurul Hidayah binti Samsul Rafzi, and now I will explain to you about the correlation between telescope and people's eyes. First of all, telescope have two parts, which are the tube and the tripod stand. So, have you ever wondered of how people could see the stars and the moon even they are so far from us? So, this is how telescope could help us. Next, focusing on the tube part, telescope has objective that pointing to the astronomical subjects like the stars and the moon, and also the eyepiece, which is what we look into. So, first of all, the rays of light which coming from the sun or the stars run parallel to each other and pass through the objective lens. Next, they will gather in focus and passing through the focal point. And after that, they will diverge again and meet with the second lens, which is the eyepiece. At this moment, they passing through the second lens. Then the light rays will become parallel again, but this time the light rays are smaller than the first parallel light rays. Lastly, they will enter people's eyes. As the result, the astronomical objects will be enlarged but inverted at the same time. But as we know, whether the image inverted or not, it will not interfere our observations as there are no top or bottom in space.
Thank you to the previous presenter. Assalamualaikum and a very good morning to all my listeners. My name is Safaha binti Mujib and today I would like to present to all of you about telescope and technology. First of all, what is invisible light? The human eye can only see visible light, but light comes in many other colors such as radio, infrared, ultraviolet, X-ray, and gamma ray that are invisible to the naked eyes. Human eyes can see only a small portion of the range of radiation given off by the object around us. We call this wide array of radiation the electromagnetic spectrum, and the part we can see visible light. By only seeing visible light, we miss out on the information conveyed by other types of radiation. Other Earth creatures can see some of the spectrum we are blind to. Certain fish, bullfrog and snakes, for instance, can see infrared radiation, which helps them find prey through murky water or in the dark. Butterfly and some species of birds can see ultraviolet light, which helps them identify certain markings on mates. When it comes to cosmic objects, key information is revealed by different portions of the electromagnetic spectrum. Telescopes are designed to capture different portions of this spectrum, providing more information than the human eye could detect on its own. There are too many types of invisible light telescope. One of them is radio telescope. What are radio telescope? Radio telescope collects with radio light wave, bring it to a focus, amplify it and make it available for analysis. We use radio telescope to study naturally occurring radio light from stars, galaxies, black holes and other astronomical objects. We can also use them to transmit and reflect radio light of planetary bodies in our solar system. This specially designed telescope observes the longest wavelength of light, ranging from 1 mm to over 10 meters long. Naturally occurring radio waves are extremely weak by the time they reach us from space. A cell phone signal is a billion times more powerful than the cosmic wave our telescopes detect. Parts of radio telescope. The antenna. The most basic antenna is a metal dipole antenna, often used on cars to pick up the radio waves broadcaster used to carry their audio shows. The most versatile and powerful type of radio telescope is the parabolic dish antenna. The parabola is a useful mathematical shape that forces incoming radio waves to bounce up to a single point above it, called a focus. Dish antenna bounce many different wavelengths at once, and we need different receivers to tune to different frequency channels for the different kinds of research we do. To observe a specific wavelength range, we select a specific size funnel to grab the radio waves we want. The diameter of the narrow end of each feed horn is the same size as a critical wavelength of the channel we want. What that means is that when the specific radio wave travels to the narrow end of its particular horn, it is beating perfectly against the sides and the horn becomes the true antenna detecting the pulse. Here, we place a super receiver to collect the back and forth pulse of the wave as a signal it can send to the computer. Feed support. We can either hang a feed horn and a receiver at the focus above the dish, or install a mirror to redirect the focus wave down into the center of the dish where we can set multiple receivers. If we place receiver at the focus above the dish, the detected signal travels by cable along the feed support structure to a point near the ground where it can be recorded and analyzed. These prime focus feeds are limited by the weight and size of the feed horn that will safely feed up there and how tricky it might be to reach them for human maintenance. More often, to get the most out of the giant dish collecting power, we use a secondary mirror called a sub-reflector at the prime focus to reflect focus wave down into a more convenient location, which is the center of the dish. Many of the sub-reflectors can be tilted to aim at the different feed horns in the center of the dish or to catch a glancing view of the sky to gather data about air quality condition. Dish surface. If the lengths of the radio wave we are studying are very small, such as millimeter wave collected by ALMA, then the perfection of the telescope dish surface is critical. Any warp, bump or a ding in the parabola will scatter these tiny waves away from the focus and we will lose information. We also have to consider the extreme environments where radio telescope may operate. Wind and temperature differences can deform the parabola of a big radio telescope dish, and the pull of gravity affects the heavy antenna as tilted to different parts of the sky. Therefore, the dishes of ALMA are kept small in order to better to control the perfect shapes under this constantly varying condition. Telescope mount. The dishes of some radio telescopes spins around a shaft that is aimed at the North Pole star. These equatorial mounts allow the telescope to follow a position in the sky as the Earth rotates, simply by copying the Earth's axis of rotation and moving against it. But large equatorially mounted radio telescopes are difficult to build because they require millions of pounds of telescope to balance at many awkward angles. The largest ever built in our 140-foot dish telescope in Green Bank. Data processing. In early radio telescope, we had to tune into single specific frequencies to watch for signal molecules of gas in space. Modern radio telescope observe a large number of frequencies all at once, with computer dividing the frequency band into as many as several thousand separate channels that may range over tens to hundreds of megahertz. This innovation has changed radio telescope from the equivalent of black and white cameras to full color.
The second one is X-ray telescope, or known as Chandra X-ray astronomy. The X-ray universe refers to the universe as observed with telescope designed to detect X-ray. X-rays are produced in the cosmos when matter is heated to millions of degrees. Such temperatures occur where high magnetic fields or extreme gravity or explosive forces hold sway. A vast cloud of hot gas in a cluster of galaxies can be several million light years across and contain enough matter to make hundreds of trillions of stars. X-ray telescopes can also trace the hot gas from exploding stars or detect X-ray from matter swirling as close as 90 kilometers from the event horizon of a stellar black hole. When charged particles collide or undergo sudden changes in their motion, they produce bundles of energy called photons that fly away from the scene of the accident at the speed of light. In fact, they are light or electromagnetic radiation, to use the technical term. Since electrons are the lightest non-charged particles, they are most fidgety, so they are responsible for most of the photons produced in the universe. The Chandra X-ray Observatory, which was launched by the Space Shuttle Columbia in 1999, can better define the hot, turbulent region of space. This increased clarity can help scientists answer fundamental questions about the origin, evolution, and destiny of the universe. The usual structure of a reflecting telescope used for oval wavelength will not work for X-ray, as they would simply pass through or be absorbed by a parabolic reflector. X-ray will only deflect off a mirror if they only graze its surface. So, X-ray telescope must use multiple mirrors at slightly increasing shallow angles to gradually deflect the X-ray onto a detector. This means X-ray telescope must be several meters long to accommodate for this long focal length. The detector used can include modified Geiger counters, fine wire meshes, or very sensitive CCDs. X-rays are unable to pass through Earth's atmosphere, so telescope must be placed on satellites in orbit. X-ray telescopes are used to study Earth, such as distribution of hot gases between galaxies and supernova, remnants which would be otherwise unobservable. Studying X-ray image can also help us to understand the age, composition, and expansion rate of the universe. Next is infrared and ultraviolet telescope. This telescope function in a very similar way to reflecting telescope used to observe visible light. Incoming waves are reflected by a parabolic primary mirror onto a smaller secondary mirror, which focuses the rays onto a detector which records the image. One unique problem of the infrared telescope is that they can produce their own IR radiation from their head, so must cool to very low temperatures. Water vapor in the Earth's atmosphere absorbs some of the incoming infrared radiation, which limits the places where infrared telescope can be used for scientific measurement. Infrared telescopes are usually built very high up on the mountains or in a very dry areas like deserts to avoid this problem. Some are placed on balloons in plane like Sophia, or even into orbit to get clearer images. Infrared telescopes are used to observe objects that are too cool to be observed in shorter wavelengths of radiation. These include planets, some nebula, and broad dwarf stars. It allows astronomers to measure the temperature of astronomical bodies and judge their composition by how much infrared radiation they absorb. It also allows us to view light from the early universe that has only just reached the Earth, which was originally in the visible part of the spectrum, but has since redshifted into the infrared part of the spectrum. Meanwhile, ultraviolet telescope, given the wavelength of UV light is smaller than that of visible and infrared light. There is even less room for imperfections, and the mirror must be even more perfectly shaped. Such like infrared radiation, ultraviolet radiation is absorbed by moisture in the Earth's atmosphere, and as such, ultraviolet telescope must be placed in orbit to make observations. Ultraviolet telescope can make observation of hot and energetic objects that don't emit visible light. This allows a more detailed study of hot stars, the processes of their formation, and the center of galaxy, for example. So for the last one is Fermi Gamma Ray Space Telescope. What is the Fermi Gamma Ray Space Telescope? The Fermi Gamma Ray Space Telescope is a NASA spacecraft. It is in a space studying the most powerful sources of radiation in the universe. Radiation is energy that is in the form of light or of moving particles that are smaller than atoms. The most extreme types of radiation is gamma rays. So, what are gamma rays? Light energy comes in many different forms. People can only see a small portion of the different types of light. This light is part of the electromagnetic spectrum. This spectrum is made up of all the types of electromagnetic or EM radiation in the world and possibly in the universe. EM radiation travels in waves, and each type has a different wavelength. So, X-ray and gamma rays all have wavelengths that are shorter than visible light. The shorter the wavelength, the more energy the radiation has. Gamma rays have the shortest wavelength, therefore they have the most energy. Gamma rays have more than 1 billion times the energy of visible light. Gamma rays have so much energy they could harm people on Earth. People are protected from gamma rays by Earth's atmosphere. The atmosphere absorbs gamma rays, preventing them from affecting life on Earth. Because gamma rays cannot penetrate Earth's atmosphere, scientists use satellites in space to study them. So, why is NASA studying gamma rays? Gamma rays come from the most extreme places in the universe. NASA is studying them because scientists want to learn more about the high energy environments in the universe that make gamma rays. Gamma rays often come from objects like black holes and exploding stars. Gamma rays sent out by objects embedded inside galaxies greatly affect the space around this object and how this galaxy evolved. By studying gamma rays, NASA can better understand how the laws of physics work in the extreme environment found in the distant universe. So, how does Fermi work? The Fermi telescope has two main instruments. It has a large telescope that finds gamma rays with 10 million to more than 300 billion times the energy of visible light. The spacecraft also has detectors that observe gamma ray bursts. Gamma ray bursts are brief flashes of gamma rays. Scientists think most of these bursts come from exploding stars that become black holes as their cores collapse. More than half of the non-gamma ray sources are mysterious. Scientists do not know what causes the gamma rays to be emitted from these sources. The information from Fermi is sent back to scientists on Earth. The scientists use the data to create pictures of the objects Fermi studies. These pictures help scientists discover the sources of gamma rays.
Right, now it's my turn. My name is Muhammad Amirul Afandi Berahmat, and I will present to you guys about the topic Basic of Handling Telescope. Alright, so for my first point is which is telescope selection. Okay, before we need to choose our telescope, we also need to know the types of telescope first. It is because there are three types of telescope, which is refractor, reflector, and catadioptric telescope. Alright, so for my first point is telescope selection. Before we need to choose our telescope, we also need to know the types of telescope first. It is because there are three types of telescope. Firstly, refractor, secondly, reflector, and thirdly, catadioptric. Okay, for the refractor telescope, this telescope is a refractive telescope that consists of several glass lenses as a tool used to capture light and perform the function of the telescope. This telescope also consists of two convex lenses, namely as objective and ocular lenses. The rays that enter the binoculars are reflected by the lens. Therefore, these binoculars are called refractive telescope. And also this model is ideal for observing the moon, planets, and offer clear image. But it is not easy to see small corps like galaxies and nebulae. So, for the refractor telescope, this telescope also known as Newtonian. And this telescope uses a mirror instead of a lens to capture light and reflect it. Reflector telescopes are widely used for the observation deep sky objects such as nebulae, galaxies, open stars, and comets due to the light gathering. And these telescopes are much better than the refractor telescope, so that objects with small light intensity can be seen with a reflector. Okay, after that we can see the catadioptric telescope. This telescope has a working system that is not much different from the two types of telescopes above. This telescope is a combination of a reflector and refractor telescope that collects media using two media to collect light, namely as a mirror and a lens. It is the best for astronomical photography and easier to carry than the reflector type, but the price is much more expensive than the other types. Alright, secondly, we need to identify the area used to place the telescope. Okay, it is because area selection is also important and needs to focus on lightning angle, area, and others. And each area and place have different conditions such as lightning. For example, choose a location for the stars to look at without tall objects such as buildings and trees that could obstruct your view. Okay, thirdly, we need to identify what you want to see. The selection of appropriate objects is also important because not all objects can be seen by a telescope. For example, if you want to see small corps like galaxies and nebulae, we cannot use a refractor telescope to see it. Alright, so we move through to the second point, which is learn telescope. Firstly, we need to learn to use this finder, which is this element is usually located on the side of the telescope and offers a large field of view of the sky than the telescope itself. For example, a telescope with 5x magnification covers an area the size of your little fingernail, while an 8x instrument offers you a field of view the size of a golf ball. Secondly, we need to get familiar with the frame. Usually, two types of telescope mounts are used, which is equatorial and altazimuth. You need to know who your telescope is in order to use it properly. The altazimuth mount can move the telescope tube vertically and horizontally, thus simplifying the operation for beginners, as it is easier than the equatorial model. And the equatorial mountain allows you to point the telescope towards the 4 cardinal points of the sky. The polar axis, which is the rotating element near the base of the telescope, must be parallel to the polar star. Next, you will be able to follow the movement of the horizon from this point, from east to west, which is following the clear movement of the stars. Thirdly, we need to learn to use a tripod, which is you must be sure that the 3 supports are balanced, otherwise the telescope could fall and break. When choosing a point from which to look at the sky, consider the need for a flat area and a floor on which to place the telescope. Alright, so for my third point is observing the state of the sky. Firstly, we need to sky study, which means that we must first determine what we want to see and need to adapt to the weather conditions. For example, if you want to see stars and constellations, we need to read text or research about it. This will tell us about the best time for observations, where and when is it easier to see the planets. You can also learn about the star map, so when we are in front of the phenomenon, we will know where to point the telescope. Secondly, we need to choose a point from which to see the sky, which means that we must be very careful in this operation, which must consider what we are looking for and where it should be placed in the sky. We also need to find an accessible place at night with a safe, flat area to support the telescope tripod. For example, if we live in a large city, go to the roof. Is it a safe place to seek shelter from the surrounding light and get a clearer image. And after that, we also need to try to avoid passage of bridges, concrete, and bitumen. The footsteps of others cause vibrations that interfere with image quality. And thirdly, we need to use an eyepiece with a minimum magnification and point the instrument towards an object around 30 meters. For example, a tree but not the sun. Do not point the telescope at the sun. Even if you have sunscreen, the tinted glass can break and you will accidentally damage your eyes. And after that, we need to center the object with the finder to make sure the image is clear. And lastly, we can switch to an eyepiece with a higher magnification and try again until we see what we want to see. So that's all from me. Thank you.
Before we end this presentation, I would like to give a conclusion. The most extraordinary development scientists made is another one. They managed to send telescopes in space. Why do they send them in orbit? The main reasons they put telescopes in space is to get around the Earth's atmosphere so that they can get a clearer view of the planets, stars, and galaxies that they are studying. Our atmosphere acts like a protective blanket, letting only some light through while blocking others. As a matter of fact, these credible instruments do not focus only on visible light, but observe other frequencies of electromagnetic radiation like UV rays, microwave, infrared rays, and gamma rays. The most famous space telescope is Hubble, that has taken the largest photo of deep space, visualizing the oldest objects we can see from Earth. So I think that's all from us. Thank you for watching.